Yeah, sure. So okay, so I'll start. Um, okay. So can you see the screen? Somebody? Yeah, sure. Okay. All right. So yeah, so we'll basically just this lecture is going to be sort of another look at DNNs. Last time we looked at what DNNs are, as this was sort of an introduction and how do you train them and all of that. Today we are going to try and see what properties DNNs have that make verification easier or challenging. What are DNNs in terms of functions, and like look at DNNs from a verification perspective, right? So just as a recap, DNNs are basically these networks of neurons, and the way they compute a value is that each neuron takes a weighted sum of the values from the previous layer, adds a bias to it, and then puts a nonlinear activation function on it to get the output value, right? And this happens at each layer and so on to until you get to the output layer, right? So we can actually rephrase this a little bit in a way that might be little bit better or easier to visualize or work with later on, which is that each input is a vector of real numbers, right? So the input is a vector of reals, and then when we're doing this sort of weighted sum and adding a bias, what this is essentially an affine transform, right? So an affine transform is basically a transform that looks like this. You take some vector, you multiply it with some linear, like apply some linear transform, right? So multiply it with some matrix, and then you add some bias vector. So you basically do a linear transform and then you shift the vector, right? So you can sort of think of it as a like affine transform. So each layer we are doing an affine transform, which is sort of this multiplication by weights and adding of bias. All of this is can be packaged together into an affine transform, and then we piecewise apply a nonlinear some nonlinear function, right? So for example, if we were to apply that, say, sigmoid, what we would do is we would take this affine transform, get some vector, and then do something like this, where by this I mean sigmoid, which is a real to real function, right? This is being applied on each component, right? So we can write the neural network as sort of these sequence of affine transforms, and then apply some nonlinear activation function, and again some affine transform, and again apply some nonlinear activation function, and so on, right? So this is basically sort of another. You could say that this is one notational way of representing neural network, right? Then this in this affine transform, this matrix that we have, this corresponds to the sort of weighted sum that we had previously, right? So okay, so I have taken vectors to be row vectors here. So if I take vectors to be row vectors, then you can imagine that this is all your components of X. This will be your matrix. Then each column here is going to compute a weighted sum, right? So we call this the weight matrix. So we have weights, and then whatever you add is corresponds to the biases, right? So again, once you've computed the weighted sum, you're just going to add some biases to it. So that is basically your biases, right? So yeah, just as a recap, so we have these weights and biases, and then if you think about your neural network as a parameterized function approximated, these weights and biases are your parameters, right? So the entries in your matrix and bias vector, so each entry here and each entry here, those will all get collected and form, like together form the set of your parameters. Okay, so hopefully, like, so everybody recalls this, right? Anything doubts or anything here so far, or anything from previous classes that you want to talk about? Okay, so if somebody says something in the chat, just let me know, because I don't have the chat open right in front of me. Sure. All right, so yeah, we also saw some of this in the first lecture, some of this motivation, why do we want to verify DNNs? And I won't go over this in too much detail, but I just have a few points here as a recap, if you will. Again, see, DNNs are, approximate. We when we train the DNN in this way, if you remember, the gradient descent algorithm doesn't give you any guarantee, right? It doesn't give you a guarantee that you'll approach a global minimum, and even if you approach a local minimum, it doesn't give you a guarantee that you'll land at the exact local minimum, right? So there is no guarantees. What you end up training is something that is ultimately approximate, right? And that means that inherently there is some like error proneness to our neural networks, and this is like very easily demonstrated using the adversarial attacks. So for example, one of the like more scary examples was this one where you had like some stop sign, and then people put like a single patch on it, and the neural network, instead of identifying this as a stop sign, it identified this as a 50 kilometers per hour limit, right? So if you imagine that this neural network was running inside a self-driving car, right, that could be disastrous. And on top of this, even though they are approximate, they are actually really good and really general tools for solving a very wide class of problems that are otherwise really difficult to solve, which means that they're actually being deployed widely, very widely. If you look at any sort of field, there is some machine learning that is getting involved in that field, and more often than not, at some point, some sort of neural networks come in, right? So if they're being deployed widely in various areas, it's only a matter of time before people try to deploy it in safety critical areas, right? Areas where an error or a bug or some inaccuracy can cause huge amounts of damage potentially to human life, right? Things like self-driving cars, things like nuclear power plants control systems, things like medical systems where you have a neural network that is probably doing a first screening, right? So that is why, we have to somehow come up with ways of formally guaranteeing some of the behavior of neural networks. The main two sort of formal guarantees that people look for when it comes to neural networks are safety. So safety is, if you have, say, a collision avoidance system and the sensors are clearly stating that there is, say it's for aircrafts, and the sensor is clearly stating that there is another aircraft to the left, right? So you have your aircraft here, and your sensor is clearly stating that there is something here to the left, but your neural network still asks your aircraft to turn to the left, right? So this is a very clear violation of safety. We would like to formally guarantee that this will not happen. Similarly, another thing that people look for formal guarantees for is robustness, right? So if you talk about the medical imaging system, if there is very slight noise, you can engineer the noise in such a way that something that is very clearly, say, a tumor, the image classification system actually doesn't classify it as a tumor at all, right? So of course, all these adversarial attacks, the noise is very carefully engineered, but who knows, like some sensor noise, some dust on the camera might actually end up emulating that. You can't deny that possibility. So it would be, due diligence to make sure that whatever network you're deploying has enough robustness that such like small amounts of noise cannot change its decision by a huge amount when the decision is very clear. So we have, such formal guarantees of robustness are necessary, right? So this is sort of the motivation behind verifying DNNs, and all of this is stuff is that we had done it in, I think, in the last to last thing. But now that we have this, let's actually state this DNN verification problem sort of a little bit more formally, like somewhat mathematically, right? So what we have is we have three things that are given to us. One is this a neural network that someone has trained for us. And then we have two sets of conditions, a precondition and a post-condition, right? So when I say precondition and post-condition, what these are basically So these are basically just some formulae that represent a set of conditions or constraints on X, right? So for example, if you consider the aircraft collision avoidance situation, then you can say that you have some property that you want to specify. Let's say that like there is an aircraft to the left, is intruder, let's say, right? So then maybe your aircraft is situated or set up like this, where you have many different, say, sensors which are sensing in these directions, right? So you have hard left, slightly to the left, forward, right, hard right, and so on. And each one of these sensors is going to give you some value depending upon how close this particular sensor thinks that there is an intruder, right? So if there's an intruder here, maybe we know that this particular sensor is going to give you some high value, right? And now all of these sensors are basically forming the input to your network. So the input to the network looks like a vector where you have each one of the components is the value of one particular sensor. So maybe this particular component corresponds to the value or the sensor that is towards the hard left side, right? So if this one is your hard left sensor, then your condition phi can be something like this, right? So it will take your vector x, and then the condition is going to be true if and only if the first component of your x vector, let's say, which is the hard left component, if that is greater than 0.9, right? So in this way you have a condition that, like, is some mathematical expression, but it essentially encodes this fact that there is an intruder to the left, right? So similarly you can have a similar situation for your post condition, right? So your post condition might be in the collision avoidance case that we shouldn't turn left. Right? So then maybe your neural network actually produces another vector which has got, let's say, 3 components, right? So depending on whichever component has the highest, like, or has a very high value, the aircraft will try to follow that particular order. So maybe there is a component that has a value for left, there is forward, and then there is right. Okay, so then if your left value is very high, then let's say that the system is such that if your left value is very high, then your aircraft is going to turn towards the left, right? So then when we say that we shouldn't turn left, we can express it like this, right? That this post condition is going to essentially be just this, right? That your first component of the output vector, it should actually be something small. So you should not turn towards the left, right? So maybe it should be less than 0.1, right? So now, if you remember, we had specified a property or a safety property for this collision avoidance situation as follows, right? If you have intruder to the left, that means that you should not turn left. Okay, so this intruder to the left is being encoded as this, and this not turn left is being encoded as this, right? And we know that this output is basically something that we get when we apply our DNN to the input. So if we combine all of these things into a single formula, this is what we'll get, right? So we are saying that, okay, the intruder is towards the left, and we are computing some output using our DNN. Then the output should not say that we are turning towards the left, right? So this is basically the general or the most general structure that we'll follow whenever we are specifying some property that we want to verify, right? So we will have sort of some precondition, and then some formula that relates the inputs and outputs in terms of the neural network. There might be more things here. You might do some other non-DNN oriented processing after to the output of the DNN, right? You might pre-process your input in some way. So all of those things you can put in here. You can have 2 or 3 different DNNs. All of that you can put into this part. So you have some relation between your output and your input, and then you have some post condition on your output, right? So this is basically the general way in which we will specify the properties. So precondition and then some relation between input and output implies some post condition, right? And how we sort of interpret is that for any x and y, this formula should always hold as true. Okay, so for any input vector, you'll get some output vector, or let's say that you pick some output vector that corresponds to that input vector. Then if that input vector actually satisfies your precondition, the output vector should satisfy your post condition, right? So is the formal specification of the property is this clear? Any questions? If not, some, yeah, okay. All right, so yeah, so now basically the next part, we're going to look at various properties of DNNs and how they affect, how they make the verification problem challenging, or how they can be used for verification and so on. But before we go into that, I'm just going to talk a little bit about various activation functions, right? Okay, so basically, so far, whenever we have talked about neural networks, we were just talking, or the activation function that we were taking was usually I just kept it as some abstract activation function, and sometimes in the previous things I think I gave the example of sigmoid, right? But the actual fact is that there is actually a very wide variety of activation functions, right? But a few things that people usually make sure when they make these activation functions, and there is some theoretical and practical reasons for that, is that these activation functions are almost always continuous. I'm saying usually here, but there you won't come across a non-continuous activation function anywhere, I think. And they are also differentiable almost everywhere, right? In fact, most activation functions end up being smooth. If they're not smooth, they'll be non-differentiable at 1 or 2 points, something like that, right? But they're differentiable, in fact, continuously differentiable almost everywhere. So we can add that actually here. So yeah, so this is basically a few, whenever you think about an activation function, you can always assume these two facts about it. So why is there so many activation functions? Because it really actually allows us to control the derivative of the final loss function that we had. If you remember from last time, we somehow had constructed this huge loss function, which is a function of our parameters, and then we were doing gradient descent on this, right? So we're using gradient descent to optimize this. So since gradient descent depends on the gradients, it's a good idea to control them, and the only sort of control we have over them at the level of constructing a neural network is if we try and control the derivatives of the neural network that we get, right? So that is essentially what people try to do when they apply various, or one of the things that people try to do when they apply various different activation functions. So you'll have a set of advantages and disadvantages which usually depend on the derivative of the activation function. So for example, if the derivatives are too small, right, or if there's 0, then if somehow you have gone to a particular configuration of your configuration of your theta here, for all your training data, the derivatives of all your activation functions are coming to be 0, right? If that happens, then you don't have any learning, right? Because in the entire derivative of this actually becomes 0, and if this becomes 0, then gradient descent doesn't take any step at all, right? So it's like gradient descent, you can visualize it as it is sort of going down a hill, right? But if you end up in a plane, then there is no hill to go down, right? So it will just stop there. So this is basically one of the situations where you would want to avoid. Similarly, if the derivatives are too large, then gradient descent might actually blow up and some minima may be skipped, right? So if you have, for example, something like this, you have a nice continuous function, then suddenly a cliff. Then when you land in this cliff, there is still a huge derivative in this direction. So maybe there was a minima here, and then something like this was happening, and this just skips all the way towards there, right? So such sudden jumps in derivatives is going to also be bad. Minima might be skipped and so on, right? So you have to control or balance these two things, and of course usually you would want your activation functions to also be somewhat like often they're bounded, which means that it's hard not to get these two situations, right? If you have a bounded function, then it's very easy to end up having areas where derivatives is too small because you have some flat region. Similarly, if you're have a bounded function, then you might, if your function is to change, it might need to change within a very small window. So then again, derivatives become too large. So such issues are there, and if you have more complicated architectures of neural networks, you have many layers, then these issues tend to get compounded, right? So any anomalies or any bad behavior you have with the derivative, they'll basically get added up the more layers that you have, right? So all of those problems get compounded, and you essentially have a situation where it's very hard to learn something in a stable way. So this is basically the perspective with which people try different activation functions in an ML context. So let's look at a few examples just very quickly. I think one of the most important examples, I think for us at least, is ReLU. And this ReLU is basically just defined as it's going to be 0 when your input is negative, and it's going to be the same as your input when your input is positive. So if you draw a graph, it looks something like this. Sorry. So you're going to have 0 over here, and then it's just going to be identity over here, right? So the good things about this is that it is actually very easy to implement, and it's very efficient to learn, because of these two things, it is used very widely. It's also really an interesting function for us because the resulting neural networks have a certain special property which allows us to analyze them easier from a verification perspective. Another activation function which we have seen is this sigmoid, right? And this is basically this formula. And if you remember, this is like we had actually used it in a situation where we wanted some probability distribution as the output of the network, right? And in such situations, sigmoids are used very commonly. Tan H is another one that is often used in certain kinds of networks, which we'll get to later on, which are called LSTMs. You don't need to worry. Like if you don't know, you don't need to worry about it right now. But if you do know, then you probably know all of this anyway. But basically, what tan H is used is it produces values between 1 and -1. So you can use that particular value as a coefficient to multiply another value, and control the effect that whatever other value you have is going to have, right? So for example, if you have such a situation, so let's say you have a network where you're essentially ending up calculating this. You have some value x, and then you're going to multiply that with some gate value g, and then you're going to add it to y, right? So if g is going to be set to 0, then the effect of x is going to just not be there on this expression, right? So let's say y prime is equal to this. So the effect of x is gone in that case. If g is instead being set to 1, then x is getting added to this thing. But if g is being set to -1, then whatever effect x was supposed to have, in this expression, it's getting reversed, right? So with g, you can sort of control the effect that x is going to have on this expression. So usually these sort of arrangements are called gates, and usually the value you feed into the gate is going to be some value between 1 and -1, and often what is used to generate that value is this tan H as an activation function, right? So the takeaway from this slide is basically that there is this zoo of like a huge number of activation functions, and there is a lot of verification methods which leverage specific properties. So we have many methods that actually can leverage ReLU, for example. So for example, with ReLU, there is a lot of ReLU specific verification algorithms. There are a huge number of them out there. And by leveraging these properties, these verification methods are, they actually try to gain some advantage over what is otherwise a hard problem. But again, on the other spectrum, there are also methods which are very general. And these are also good because then you don't need to actually worry about what activation function does your neural network have. Can I use this method? Okay, my neural network has got this particular activation function, which means I cannot use this method. So there is a lot of value in general methods as well, right? And we'll see both of these methods in later things, both of these sort of varieties. Okay, so this was sort of a detour, and I wanted to talk a little bit about activation functions just to concretize and at least give you 3 examples of it. But yeah, now I think let's go into some properties of DNNs and how those properties affect the verification problem, right? So, any questions so far? Bef- Before I move on, I guess. I mean, people who've seen neural networks, all of these things is again will probably be uh, like okay to you, but there are a few people who haven't seen neural networks, I think so. Um, so I guess there's no doubts in okay. All right. Okay. All right. So now let's come to some properties of DNNs. So there is this one class of properties which I'll just call smoothness properties, but basically the properties that these properties are very useful for ML algorithms because they depend on such properties. But the idea is that like if your activation function is continuous, then the DNN is going to be continuous, right? Similarly, if the activation function is differentiable, then we know that the DNN is also going to be differentiable. Because remember, if you don't have the activation function, your DNN basically just looks like this, right? You have your X, you do some affine transform, right? And affine transform is all sorts of niceness, right? Like affine transforms are continuous, they're differentiable, they're smooth. So you don't have any issue here. But then you do a piecewise application of some activation function, right? Or sorry, some pointwise application of activation function. And here is where any sort of non-continuity or non-differentiability or non-smoothness, anything that any such issues that might creep into your entire network, the only point where it can creep in is in this activation function. So as long as your activation function is nice, your network is also going to be nice, right? And like we saw, usually and like these activation functions are continuous and they are differentiable at least almost everywhere, right? So which means that usually DNNs you can assume to them to be continuous and differentiable almost everywhere objects. Okay, and this is really important for gradient descent, right? Because with gradient descent we sort of assume that we can calculate a gradient at any point. But like if that assumption doesn't hold, if you're like whatever L that is that you're optimizing, if that turns out to be something that is not continuous, then you can't optimize it with gradient descent. Similarly, if you have an entire region where you can't calculate a derivative, then you're in trouble, right? But turns out that if you're differentiable almost everywhere, that is good enough because say for example your loss looks like this. There is some non-differentiability point here, right? So now if you while doing your gradient descent, if you don't hit this point, then there is no issue, right? So maybe you start from here and then you keep descending along this and so on, right? But if you're unlucky that you actually hit the point of like where there is no gradient, then you can always just, since you can't calculate any gradient, you can always just maybe shift randomly in a particular direction. Now of course this will again, like if you shift in the wrong direction, you might end up with something that is a local minima but not a global minima, but that problem was there in any case. So it's not like we are introducing a new problem by doing this. But because our function is differentiable almost anywhere, we know that the probability of starting from a point where there is no derivative and then shifting and ending up with another point where there is no derivative is really low, right? In particular, there cannot be any region of points where any point inside this region doesn't have a derivative. So if you have such a region, then this differentiable almost everywhere criteria doesn't hold, right? So by definition, if we do this shifting, the probability of us ending up with another point where there is no derivative is vanishingly small, right? That is basically the definition of differentiable almost everywhere. So you can then say that with almost 100, like with vanishingly large probability, okay, with vanishingly small probability your gradient descent algorithm will fail, right? So the probability of a gradient descent algorithm actually getting stuck in these points where there is no derivative is going to be very close to zero, right? So with these sort of like conditions are really important for ML algorithms, but they're also actually really important for verification. We can use them as well. So the people who train neural network, they depend on it. We can also leverage them as people who are trying to verify neural networks. So for example, one of the intuitions or one of the facts that you can sort of leverage is that if you have, since you know that your neural network is continuous, and usually if you notice these things, the precondition and the post condition, these are also, you know, regions that are like level functions of some continuous or level sets of some continuous function, right? So for example, if you look at this, let me just come here, I guess. Yeah, so if you look at this, say x naught is going to be less than 0.99 or 0.9, right? So then this is actually a level set of the continuous function x naught, right? So if we imagine that this is the space of all x's, then this the region that actually satisfies this, it's going to form some set like this, where you have, you know, contiguous sets of values, right? It's not going to be some dense or scattered set of points like that, right? It's going to be instead be a region of a solid region of contiguous set of points. I think, yeah. So this is basically, since we know that this is the case, then if we have some counterexample to our property, so if an input-output pair is bad, right? So for example, if you have, say, somehow found that, okay, for this particular value of, say, input, you know, your precondition is satisfied, but your output condition is not satisfied, right? So then, since your entire function is continuous, you know that there has to be some region. So let me just draw this a little bit bigger. Yeah, so you have, this is, say, your inputs, and this is, say, the preconditioned region, right? And you have now found a particular point here which is satisfies the precondition but doesn't satisfy the post condition, right? So that means that that particular point is represents a violation to your property, right? So then what we know is that, like, we will have a region around this point where any other point is also going to violate this particular property, right? And you can actually, like, come up with particular constraints on your precondition and postcondition which end up being very reasonable, and you can prove this particular fact. This is like, you know, basically using just some simple like real analysis sort of stuff, you can prove this. So an intuition behind this would be that, you know, the post condition is also going to be some set. Let's say that if it's on the, like, it's also 2D, it's going to be something like this. So you know that since they both of them are solid, unless you've ended up picking a boundary point, then you know that there has to be a ball around this where, you know, precondition is satisfied but post is not satisfied, right? So post is not satisfied, right? So there you can basically sort of put very reasonable constraints on your precondition and post condition and actually prove this fact. But intuitively, is this clear? Or yeah, so if I were to say, ask you to prove this, can you, like, sort of think of a way that you would actually prove this? That if you have a bad or say if you have a violation, then you'll have some ball around it which is also violations of your property. Yeah, right. So okay, so that would be, say, something that you can maybe, like, if you do get some time to, like, try this out as an exercise. Right, and the important point is just to, like, state this in a more rigorous way, because like what is the exact condition on the precondition and postcondition for this to be true. Of course, you can, if you have some pathological phi in psi, then you can't prove this, right? So what is the what is a reasonable constraint on the precondition and postcondition functions for which this will actually be true, right? You can assume that your DNN is continuous and differentiable almost everywhere. Okay. So these are some properties of DNNs that we can leverage. Some other properties are so if you think about the activation functions that I showed you, right? Let's look at these things. So for example, with say, even if you look at something like sigmoid will usually look like something like this, right? So for really negative values, it's just going to be very close to 0. And then it's going to increase like this. And then for positive values, again, it's going to be very close to 1, right? So these functions, there are actually regions in which their behavior becomes very close to being linear, right? So for example, if you consider this region, then it is linear in the sense that it's just a constant function, right? It's very close to being a constant function. Similarly, over here also, it's very close to being a constant function, so it's technically linear. And then you can also have a very small region around 0 where it also behaves somewhat linearly, right? So these functions actually admit very well to linear approximations, right? So there are ranges of values for which they become almost linear. So then if you imagine, like if I say make this sort of a little bit tighter, let's say that I split my, like I have 3 such regions, right? And these regions I've made them somewhat tight, and I have made sure that my bounds are good and so on. So I've got 3 such regions. So region number 1, number 2, and number 3, and I have somehow, like, you know, up to some measure of accuracy, these things are almost linear in these regions, right? So it's almost linear up to some epsilon, let's say. So then, if my inputs is such that all of the values that are being fed into each one of the activation functions all across the DNN, they fall in either this region 1 or 2 or 3, then the entire behavior of the neural network will become almost linear, right? And you'll have regions of input values where this sort of a situation will happen, right? So let's consider just region number 1. Okay, so region number 1 looks like something like this. They say that your input to the activation function, if you call it x, let's say that it's less than something like 1, right? Maybe. I don't know what this constant will exactly turn out to be, but let's just say for now that there's something like this, right? So what does that imply in terms of the neural network? So remember that, you know, you'll have some networks that are coming from, or some nodes that are getting their input directly from the input layer, right? So then what we're saying is, okay, this input here is actually going to be less than 1, or less than minus 1, sorry. So less than minus 1, right? Similarly, the input here is going to be less than minus 1, input here is going to be less than minus 1, right? So that will correspond to some linear condition on your inputs, right? So what we're essentially saying is some set of, some conjunction of constraints like this, right? So if your inputs are x0 and x1, we're saying that x0, w0 plus x1, w1 plus b is less than minus 1. And then you'll have to repeat this for multiple such values of x, w0, w1 and b for each one of these neurons here, right? So you have such conditions, and then, you know, these conditions will again get cascaded. So if you have these things as the input to the next layer, you can write such conditions in terms of that, and so on, right? And if you combine all of them together, what you'll end up getting is some solid region within which all the values of all of the activation functions are going to lie in region number 1, right? So does this make sense to everyone? Should I maybe like write out some more details here? Yeah, sure. So let's take this sort of a situation, right? So now we have let's have some numbering. So let's call this the inputs x0 and x1. Then let's call these as y0, y1, y2, and these as z0, z1, z2, right? So now what we know is that y0 is basically going to be the input to x0, the input to this particular node's activation function, right? So what we can say, or what we need to say, is that y0 is going to be less than -1, right? So if y0 is less than -1, then this particular node lies in a region number 1. So then what we can say is, okay, y0 is equal to, let's say, w 00x0 plus w 01x1 plus b0 y0, right? So then what we can end up saying is w00x0 plus w01x1 plus b0, sorry, there's no y0 here, is going to be less than -1, right? So then if we have this, so we have this, remember this we are getting from this particular node, right? So we're getting this particular node by considering these two sort of edges here, right? So similarly, we'll get another such thing for this node. So we'll get maybe w10 x0 plus w11 x1 plus b1 is also less than -1, right? And then similarly for this node we'll get a third condition, w20 x0 plus w21 x1 plus b2 is also less than -1. So now we know that if our x0 and x1, which are our input, right? So if input satisfies these three conditions, if all these three conditions are satisfied, then we know that y0, y1, y2, all of these are in region 1. Right? So is that okay? Hello? Hello? Right, sure. So remember, what we're trying to see is that, what we're trying to prove here is that, like, this particular this region 1 that we had, right, which is given by input to your activation function is less than -1, we're saying that what we're trying to show is that there is a region of inputs to your neural network where everything, all of the activation functions are going to satisfy this. Sorry, 1 second. Yeah, sorry about that. So let's forget about the next layer. Let's that your neural network has got the one hidden layer, right? So now what I'm basically trying to do is I'm taking the condition that the input to all of the activation functions in these nodes is less than -1 and trying to express that in terms of the input to the network, right? So the input to the network is x0 and x1. The input to the activation functions in each one of these nodes is y0, y1, y2. Maybe I could write it even a little bit better than this. So we have x0 and x1 going into the network, and then we have, you know, the linear layer, right? So that gives us y0, y1, y2, and then these are going through some activation function, right? Yeah, so I'm saying that if they're less than -1, we know that the activation function behaves close to linear, right? So that is basic. Yeah, so we can always like sort of engineer such regions, right? Again, -1, the specific value might not be, you know, correct, but like if you imagine the graph of the sigmoid function, it looks something like this, right? So then there'll be some constant for which below that, you know, you can like for any given measure of closeness, you can say that it's very close to linear, right? So maybe you can fix an epsilon and say that okay, if y, or let's say that yeah, so if yi is less than minus 1, let's say that these are z1, z2, z3. If yi is less than minus 1, then that implies that zi minus yi, or let's say that zi, yeah, zi minus yi, or okay, so we can maybe even say that zi is less than epsilon, right? So it's very close to being constant towards 0, right? But epsilon is something, some small number which is greater than 0, right? So we can come up with such bounds for, say, the sigmoid function. And again, you know, the exact value here might be different, and it will depend on what epsilon that you have chosen, like what you've chosen and so on. But you can come up with these things. And then once you've come, like you have that, then you can sort of convert that into a set of constraints on the inputs, right? So remember that y0 is going to be this. So this entire y0 is going to be just some weighted sum of the inputs plus some bias, right? So y0 is going to look like this. Does that make sense? Yeah. And also this makes sense, right? Like again, you can like actually figure out what the exact values of the constants will be, but the fact that such constants exist makes sense, right? Hello? Okay, sure. So then what we know is that like y0 is again going to be some expression like this, and we had the condition that y0 is less than minus 1, so that translates to, you know, this particular expression involving x0 and x1 being less than minus 1. You can now repeat the same thing for y1 and for y2, and you'll get again some conditions on x0 and x1, all of them being less than minus 1, right? So now what you have is you have got three conditions on x0 and x1, three linear conditions on x0 and x1, and if all three of them are satisfied, so let's say that all three of these are satisfied, that will imply that y0, y1 and y2, all three are actually less than minus 1. So maybe all of these things are less than minus 1, which means that all neurons in your first layer are going to be in region 1, right? Is this okay? Yeah. So this is basically what I'm saying. And then if you were to actually plot this particular condition, this is essentially going to look something like this, right? So maybe this particular line, so this is the first line, let's say that it ends up looking like this, and then the second line ends up looking like this, and then maybe the third line ends up looking like this, right? So what you'll end up with is you'll end up with a particular sort of region in your space within which everything is actually going to be like any point that you pick over here, it's going to end up being some point which causes these three to be less than minus 1, which means that your all the neurons in your first layer are in region 1, which means that your first layer actually behaves very close to being linear, right? It's like epsilon close to being constant in our case, but that's a generalization of linear. So, or linear is a generalization of constant. So so yeah, so any point in this sort of a region, it's going to behave very close to being linear, right? Is this okay? Yeah. So now what I claim is that like this I've showed in some detail for a network with one layer, but what I'm claiming is that you can actually do it for a network with any number of layers, right? And I think I don't want to go into like writing out another layer here because I'm running sort of out of time, but you can think about that, and otherwise we'll look at this in we'll look at some techniques which basically exploit this later on, so then maybe we can talk about it. But essentially, my claim is that like if you have such regions of linearity in your activation function, so let's say region number one, even if you have a much more complicated network with many different layers, right, and much more neurons, all of this will still go through. You'll still end up having some region in your input which is maybe going to look more complicated, right? It's going to have more boundary edges and so on. So maybe it's some really complicated region like this, right? But you're still going to have some region in your input where all the neurons in all your layers are in region number one of the activation function, which means that your entire network is going to behave close to being linear, right? Does this make sense? Or can you at least swallow this? Hello? Yes, I'm saying that like take this idea and you can sort of, I showed this for a simple network with two layer or one hidden layer, right? What I'm claiming is that if you have multiple hidden layers, this still works and you'll still sort of get these regions in your input space. So this is a region in your input space where if you take any point, that particular like point is designed or that particular point will be such that all the inputs to all your activation functions in all the layers are going to be in region number one, right? So I'm claiming that you can do this. Like I showed sort of like showed it in some detail for a network with one hidden layer, but I'm claiming that this actually generalizes to any sort of more complicated network. And then since they are all in this region 1, again what's going to happen is that your network is going to behave epsilon close to being linear, right? Because this layer is in region 1, so it behaves sort of linearly. This layer is also in region 1, so it behaves kind of linear. This layer is also in region 1, behaves linear. And you're composing all of them, right? As functions, you're just doing function composition here. So if they're epsilon close to being linear, then the composition is going to be, it'll be a different sort of measure of closeness, but it'll be close to being linear up to some measure of closeness, right? Does this make sense? Yeah. Sure. So basically, then the intuition that I'm saying is you can sort of think of your neural network's behavior as this way, that your input space actually has got these regions in which your network is going to be linear, and then there are non-linear boundaries between these regions, right? So the input space has got these nice regions where your network is very close to being linear, but there are non-linear boundaries in between them. So you can think of your network's behavior intuitively as being this, right? Now the most interesting thing is that if I actually look at a particular activation function. Oh, by the way, does anybody have any like issues with this intuition? Is this intuition clear to everyone now? Hello? Yeah, okay, sure. So now if we look at this particular like activation function, which is ReLU, then notice that this actually becomes an exact characterization of your neural network, because see, the ReLU function is piecewise linear, right? So ReLU, if you look at it, the ReLU looks like this, right? So it's precisely some linear function, or specifically 0 for anything that is less than 0, and then it's precisely just your identity function for anything that is greater than 0, right? So the ReLU has got exactly these two regions, and these two regions are, they touch each other, where it behaves exactly linearly. So it's not an approximation. There's no epsilon involved here when we talk about ReLU, right? So the idea is that for ReLU DNNs, they behave precisely linearly in each one of these regions, right? So for ReLU DNNs, these pieces are going to be exactly linear, and your entire DNN is going to behave as a piecewise linear function, right? So basically, this is the idea here, right? So is this clear? Yeah, and of course, like what I said was, not exactly a proof, right? It is some sort of intuition and sketch of things, but yeah, you can actually sit down and prove this by doing an induction on the number of layers. Um, you can prove this for ReLU DNNs. You can also prove this epsilon, you can also come up with the proof for this epsilon closeness to being linear in a similar manner, right? But like I'd say that sit down and at least sort of sketch out a proof of this. Like at least convince yourself that if somebody asked you to do this, you can do it, right? So yeah. So no questions so far, right? Then I have a few more slides which I'll have to. Hello, any questions? Okay, sure. All right. Okay, so now let's talk about some high level ideas regarding, now that we know, so have some handle on what a neural network is. It's still not really clear why the DNN verification problem is challenging, right? Like, I mean, okay, it's some piecewise linear function, or it's some function that is non-linear and then very close to being piecewise linear. That is somewhat nice, right? So then why is DNN verification challenging at all, right? So let's look at why program verification, or let's relate, like we'll look at it this sort of the challenges involved in neural network verification from three perspectives. One is by trying to relate it to program verification, and then there are two perspectives which are like not related to program verification, right? So if you try and relate to program verification, then you see program verification is very challenging, right? So in fact, in the most general program verification problem, they are actually undecidable. Like, if you consider the halting problem, that is a program verification problem, right? Then that problem is actually completely undecidable. So in general, if somebody gives you a program and then some property, something like a precondition and postcondition, if you replace that neural network there with an arbitrary program, let's say some Python code that takes in your input X and computes some Y, and then in general, like trying to verify that, trying to proving that is actually undecidable. Like it's a proven fact that you can't write a program to do it automatically, right? So in that sense, program verification is hard. But then with program verification, we still have certain things that we can make use of, right? So one of the key things in programs is that they have some structure. For example, they'll have loops. So you can do things like you can do induction on loops. You can move your statements around in the loops, right? You can, maybe split your loop into two parts and then do induction on, like make some sort of an induction argument where you have some induction hypothesis that discharges one part and then the other part is simpler, right? So you can do that. You have branches. And with branches, you have, again, some set of techniques that you can apply. Maybe those two branches, like one of the branches, you can say that, okay, the program actually never takes this, so you can get rid of that, and so on and so forth, right? So this sort of structure, and, programming languages are designed in a way that this structure makes some logical sense to us humans, right? So this same structure we can, exploit from a verification perspective. Similarly, the programs are also modular. They're usually split into functions and such things. So then, if you have, like, say, a program that is split into multiple functions, you can maybe divide the entire verification task into verifying simpler things for each one of the smaller functions and then combining that, right? Finally, programs are designed by humans. So they have some, like if you take any program that was written by someone, they'll have some simple underlying logic because, somebody came up with it, right? So the person who did come up with it, he had some logic. And, since humans can only come up with so many programs, you can sort of like get really good heuristics and techniques that can really handle programs that use a certain kind of logic very well, right? So you have all of these things that are, you can use in program verification, but you don't have any of these in like neural networks, right? So DNNs are in fact black boxes, and in fact that's by design in some ways, right? Like the reason why we can apply DNN to any particular field without having too much domain knowledge or without having to think about like hard things in a very granular level of detail is because DNNs are really effective and they're black boxes, right? But what that means is that there's very little structure in the sense that a program has structure, right? There is almost no modularity in a DNN. Like you can't like really take a DNN and split it into two simpler DNNs very easily. Like you can, but that will be a non-trivial thing. That's not something that you can just look at the DNN and do it, right? And of course, there is no sense of design. There is no human sat down and decided that okay, my program is going to, or my DNN is going to run because this layer does this, that layer does that, and so on, right? All of that happened somehow automatically during training, and it might be really complicated, and it might be something that we can't really look at the DNN and make use of, right? So all of these techniques, this rich line of work that has really been going on since 1980s at least, and even like far before that, I think there's this really mature field of program verification, but very little of that can actually be carried over to DNN verification. And comparatively, DNN verification is new, right? So DNNs haven't been around like not nearly as long as programs have been. And even though there is a lot of work that is going on here, it's still essentially, you can think of it as a new field. So you can't really like say that, there's still not really a very rich set of tools that we can use for DNN verification. And the tools that we have for program verification, they don't really translate at all, right? So this is one of the ways in which it's challenging. But, you can say that the situation was sort of similar for program verification as well when it started out. So that why is that this sort of disheartening in any sense? Or you can ask another question, which is, okay, we know that programs are really expressive, and that makes program verification undecidable, right? The reason why program verification is undecidable is because programs in general can really be very complicated in terms of functions, right? If I give you a Python function, then that Python function can be like potentially arbitrarily complicated, right? But what about DNNs? I mean, maybe it's not that hard with DNNs, right? Maybe because DNNs are just these almost piecewise linear functions, then we can actually use DNNs very much more easily, right? Maybe it's not that hard with DNNs. Maybe DNN verification will actually turn out to be easier than program verification. Well, okay, but how complicated are DNNs as functions, right? Well, it turns out they can also be arbitrarily complicated under approximation, right? So, in fact, sufficiently complicated DNNs can approximate any function, and this is sort of formally stated in this particular theorem that is called the universal, or this collection of theorems, let's say, which are called the universal approximation theorems. But the gist of this is that you can take sort of a nice enough activation function. I won't go into the details because sort of running out of time, but there is some definition of nice enough. So you take some nice enough activation function, and then you're given any continuous function, and you're given any epsilon, small epsilon that is greater than 0. Then you can construct 2D DNNs which actually approximate this function up to epsilon, right? So the first DNN is going to have only one layer, but that layer is going to be arbitrarily large. And then you can also construct another DNN that is going to have layers of bounded size. So each layer is going to have only so many neurons. You're going to have some bound on the number of neurons, but the depth can be arbitrarily large, right? So if you let me make the network as wide as I like or as deep as I like, if I'm allowed either of those two freedoms, no matter what function that you've given me, however complicated it is, I can actually approximate it as close as you want me to approximate it, right? Like I can give you a network that approximates this as close as you want. So this is essentially analogous to asking, say, what all functions can a program capture, right? And if you take, say, the theory of computing course, you can like see that there is some characterization of the kinds of functions that a program can capture. And of course, this is a much more different flavor of characterization, in the sense that we are looking at things are under approximation. Things are only getting approximated up to some epsilon. But this does mean that you can actually capture very, very complicated functions, right? Because really complicated functions are actually continuous, right? Functions that we don't have any handle on are like, there are several functions which we don't have any handle on, theoretical or mathematically speaking, they are continuous. And if you have a large enough network and any small epsilon, you can always throw a DNN at it and approximate it, right? So you can imagine that, like, given a large enough DNN, that DNN can, like, if somebody has given you a very large DNN, that DNN can in fact represent some really, really like complicated function. You can't, like, just because they turn out to be almost piecewise linear, that is actually not a simplification. Realistically speaking, it might be that it actually is very close to being some really complicated function, right? So in this sense, DNNs are expressive. So this is another sort of intuition as to why this problem is hard, right? Because if your DNN can actually like be some really complicated function, that it's actually talking about some function that is really complicated underneath, then you would expect that to sort of give you some sort of guarantee about the DNN. It might actually translate into a guarantee of the function, right? So if your DNN is epsilon close to fx, and if I have, say, so if say this holds, and if I have something like phi x and y equal to n x implies this, sorry, and if I know this, then that might actually translate into some like some similar such bound for f, right? You might actually be able to replace your n with f over here, depending upon what these are, right? And f can be any continuous function. So if imagine if you have like a tool that can actually do this very fast, then that would be absurdly powerful, because then you can like take any complicated function f and prove arbitrarily complicated things about it, right? So this is another way in which DNN verification we expect it to be hard, and we expect that we won't get like any good solution to it. Okay, so these are the theorems. And finally, the final third perspective is that DNNs are complex, right? So what do I mean by that? See, in terms of being expressive, there are actually a lot more other classes of functions which are not as complicated as DNNs, which are as expressive, right? So one example would be polynomials. So if I give you any continuous function, and this is a sort of a well-known theorem, I think it's called Stone-Weierstrass, but if I give you any continuous function and they give you any sort of epsilon bound around it, so there's some epsilon bound, and this is an epsilon region around the function, then you can actually always find a polynomial. Okay, so all of these functions are on a compact domain. That is one technicality, but yeah, so if you don't know what that means, it's fine, you can just ignore it for now. But you're going to find some polynomial that is actually going to be epsilon close to this particular function, right? So if you give me any epsilon, I can actually give you one such polynomial. So in that sense, polynomials are also expressive, right? So you can ask me that, okay, if polynomials are also expressive, then polynomials are very easy to analyze. Polynomials are things that we understand very well. So why is just because they're expressive, why are neural networks so like hard to analyze? And here's where the third sort of measure of why this thing is hard comes in. It is that DNNs are complex in the sense that if we add more and more neurons then to a DNN, then the complexity of the functions it can capture will be exponentially more. So by the way, is it okay if I just take 5 more minutes? Hello? Hello. Yeah, that was a disaster, wasn't it? So where did you guys sort of lose me? I didn't realize that. Yeah, yeah, I didn't realize that I got disconnected and kept on going in some sense. Yeah, sure, sure, sure. But there's no one else here. So do you think people will like? It's already like time is, yeah, time is up. So I don't think people will join back if we do this, right? I guess we'll just continue from next time. Hmm. Yeah, but like, where were you last time? Where did we stop? Did we go? Did I? Was I here when we? Okay, I see. Was this one done? Right, right, right. Okay, sure, sure, sure. This here is where. Okay, okay. All right. Okay, sure. Yeah. Um. So, I guess next time I'll just do this and then move on to logic and all. Okay. Sure. So, if you do you have any questions or anything that you want to ask? Otherwise, I'll just go, I guess. Okay. Sure. All right. Bye.